Hello everyone, welcome to this new video on implementing logistic regression using PyTorch. In the previous video, we saw how we could implement linear regression using PyTorch, and in this video, we're going to talk about logistic regression. So before going into the implementation, we'll first understand what a logistic regression is. So logistic regression is basically a classification task with binary classification problem. It outputs either 0 or 1. The hypothesis function is basically f equals to wx plus b, which means weight times input plus some form of bias, and then we apply a sigmoid activation to the hypothesis output and basically get the result there. So while implementing logistic regression in PyTorch, we basically need to work with 3 steps. First of all, we need to design our model where we define our input, output size and forward pass. Then we construct our loss and optimizer, and at the end we build our training loop. In the training loop, we first do a forward pass where we compute prediction and loss, then we do a backward pass where we compute our gradients, and then we basically update our weights. So let's dive in to the implementation here. So we'll import a few libraries. Import torch torch.nn as nn, import numpy from sklearn, import datasets. We'll be working with the breast cancer classification dataset from sklearn.preprocessing, import standard scalar from sklearn.model selection, import train test split. So these are the libraries that we need here. Now after that, what we're going to do is we're first going to prepare our data. We'll use our breast cancer dataset here. So let's say data equals to datasets dot load breast cancer dataset here. Now we'll split our input features as well as our target variables here. So let's do x comma y equals to data dot data comma data dot target. We'll see the number of samples here, number of samples and number of features equals to x dot shape. Let's print these out and see the values, number of samples and number of features. So the total number of samples that we have are 569, and the total number of features, input features that we have is 30. Now what we'll do is we'll do a train test split. For this, I define a variable called xtrain, x test, y train and y test equals to train test split x y. Will give a test size of maybe a 0.3. We'll do 70% training and 20% and 30% on testing, and we'll give a random state. Let's say let's say 1 to 3. Okay, now what we want to do after this is we want to scale our features here. So the 30 features that we have here might be on a very different scale range. So we want to bring it to a standard scale range and then apply those features into our model here. So for that, we have imported our standard scalar from sklearn.preprocessing. So we'll scale our features here first. So sc equals to standard scalar that we have imported. Now xtrain equals to sc dot fit underscore transform x underscore train. So it will bring my training features into a suitable range, and then I'll also do a scaling for x test, but what I'm going to do here is just to transform and not fit, because the fit task is already done with xtrain, and then basically on the range those training data are scaled, I'll scale my validation data on the same range. So I just need to do x underscore test just to transform on x underscore test. Now after this, I'm going to convert my data to tensors because I need to fit it in PyTorch. So for that, what I'm going to do is xtrain equals to torch dot from underscore numpy x underscore train dot as type np dot float 32, and then do the same for x test. So x test. Now I'm going to do the same for y train and y test. So let me just rename these x to y, and I'm done. Y, I think it's small y there, so y, and it's done. Now I can just run this. Okay, so something is wrong here. Oh, np is not defined. Oh, sorry, import numpy as np. Let me rerun this again. Okay, correct and correct. Okay, what I'm going to do is, if I see the shape of my y tensors, if I see y underscore train, the shape of my y tensors are as follows. I'll also do y underscore train dot shape. Okay, so torch size 398. What I need to do is I need to reshape these y tensors here. So for that one, y underscore train equals to y underscore train dot view y underscore train dot shape 0, 1, and I'll do the same for y underscore test. Y underscore test. Sorry, this should be okay. Yeah, now it's correct. Now what I want to do is I want to define my model. Now, as I showed you in this article, my hypothesis is f equals to wx plus b or z equals to wx plus b. I need to define that and then apply a sigmoid activation to it. So for that one, what I'm going to do is I'm going to define a class. Let's say lr. Just write lr and then dot module. I'll have an init function here. Now self, number of input features. I'll have a super method lr self dot init. After this, I need to define a linear layer. So self dot linear equals to nn dot linear number of input features, 1. I'll also have a forward function with self and x as its parameters. I'll have y predicted equals to, now I'll write my sigmoid activation function here. So sigmoid self dot linear and my input is going to be x, and I'll return y underscore predicted. So this is my model. Model equals to lr n underscore features. Okay, now I need to define my loss and optimizer function. So first of all, I'll define a learning rate. Let me write 0.01 for now. We'll do it with 0.01 and then we'll change it in the training loop if we don't get the desired accuracy that we have. Criterion equals to BCE loss, which means binary cross entropy loss. Basically, we're dealing with binary classification. So for that, will use a binary cross entropy loss, and then optimizer equals to torch dot optim dot sgd, stochastic gradient descent optimizer. And the parameters, we only need to give model dot parameters and a learning rate, which we have already defined here. Okay. Oh, sorry, BCE loss comes from nn dot BCE loss. Oh, one more typo here. So parameters. Okay, now what we do is we define our training loop here. Training loop. So in our training loop, let me first define a number of epoch. Let's go until 100 epochs, and in each epoch, for epoch in range num underscore epochs, I'll first define my forward pass here. So y predicted equals to model, and here I need to give xtrain num epoch. Okay, so this will be my forward pass. I'll also have to calculate my loss here. So loss equals to criterion, and inside this I need to give y predicted and y underscore train. Based on that, my loss will be calculated. I then need to do a backward pass. For that, you don't need to do anything, just write loss dot backward and PyTorch will handle everything for you. After that, we need to optimize or update our parameters here. So for that, again, we don't need to do much, but write optimizer dot step, and again PyTorch will handle everything for you. And after each epoch, we need to reset our gradient value to 0. So for that one, again, we need to do optimizer dot 0 underscore grad. Now we'll print our training result here too. So if epoch plus 1 mod 10 equals to 0, what are we going to do? Mod 10 equals to 0. Okay, so we'll print f epoch. This will be my epoch plus 1, and my loss and my loss equals to loss dot item, and we'll just leave it as it is. Okay, so my bracket here has been wrong. Okay, seems to be correct. Now let's train this and see what we get. Okay, so we have trained it until 100 epochs, and our loss seems to be reducing from 0.44 to 0.24. What happens if we increase our training epoch? If we go to 200, does it make a significant difference? Let's see. Okay, it does make a significant difference here. So we go until 0.155. There's still a small margin on loss that we can improve. Let's go to 300 and see if the loss comes down more or not. Yeah, so it's pretty much down to 12 since here. So I think it's kind of end to it. It can't improve much more than this with this value of learning rate. So we'll also see what happens if we increase our learning rate. So we'll try with 0.1 once in 300 epochs. Now we'll see if our value, okay, now a loss value goes down pretty down. Okay, that's nice for the training part, but we'll also need to evaluate and see how our model works with our validation data. So for that one, we'll define our evaluation part here, evaluation. So for evaluation, we don't need to do much. One thing you need to remember always while doing an evaluation is you need to begin with this one, with torch dot no grad. Now during evaluation you don't want to change your training weights, because once you have your final weights, you're basically validating your data based on those final weights. So you don't need to make any change on your gradient value. So you'll need to do this with torch.noGrade. Now y predicted equals to model. We have our final model. We'll pass our x test here. Y predicted, let's say final or something, equals to y predicted dot round. Now we'll print our accuracy here. So for accuracy, what we need to do is y predicted final dot eq equals y underscore test dot sum divided by float, and here we divide it by our total y test value. So y test dot shape 0, and we print our accuracy here. So let's just print our accuracy value here. Okay, so we'll see what happens. Okay, our model has an accuracy of around 98.83%, which is pretty good. Let's do one final change here. Will not change our learning rate because it seems to be working well. What we'll do is we'll try and change our epoch. Let us go to 500 epoch and see how it responds here. So let me retrain everything again. Okay, sorry, no, it did not retrain from the very beginning. So what I need to do is I need to run it from the model itself, because once the models and its weights are already saved, so the epoch started with the loss 0.07, which was the last loss that we had. So we'll need to start it with model. So now training loop. Okay, so even if we go to 500, it doesn't seem to improve much. It changes by a very small margin, so I think 300 is okay. Let's also test our accuracy. We had 98.83 earlier. Okay, it's again 98.83. So there was no significant change in the accuracy on our validation set, even if the loss on our training set went down by a very small margin, and the accuracy on our training set increased. So yeah, this is all about implementing logistic regression with PyTorch. You can play around with these learning rate and this number of epoch, which are basically the hyperparameters for this model here. And I guess this is it. So thank you for watching. If you have any problem or if you don't understand anything, please comment down below and I'll try to help you out. I'll be back again with some other content in the next video. Until then, bye bye, see you.